Hello everyone, this is part 2 of topic 12, 13, and 14, and last time we looked at Maclaurin series, and we had to express a result in summation notation, so a couple things we had to pay attention to was preserving powers and factorials, but it was just as simple as an exercise of taking some derivatives, evaluating most functions at 0, and then substituting them into our definition. And I guess the hard part may be to get this summation notation. But now we're going to look at Taylor polynomials. And with Taylor polynomials, we're not concerned about preserving powers and factorials. So the definition for a Taylor polynomial of the third order is we use p sub 3 of x, and it's equal to, because we're going to evaluate it at a value sometimes other than 0, the formula is f of c plus f prime of c times x minus c, then plus f double prime of c over 2 factorial times x minus c quantity squared, and then plus f triple prime of c over 3 factorial times x minus c quantity cubed. And we could stop right there. So we're not interested in an infinite polynomial, just the first, in this case, 4 terms, so up to the third derivative, and that's what the order represents. So now it's just a matter of finding 3 derivatives no matter what. So we're going to set it up the same way. We'll have a column with the function and its derivatives, and then another column with those evaluated at the value of c, in this case 2. Okay, we'll worry about that after we take some derivatives. So f prime of x, well, in order to differentiate 1 over x, you probably want to rewrite it as x to the negative 1. So negative 1, x to the negative 2. Let's continue. F double prime of x would be positive 2, x to the negative 3. F triple prime of x. Okay, normally here what I would do is express this as not negative 6, but negative 3 times 2, because I would want to preserve that factorial that's being generated, because 3 times 2 times 1 is 3 factorial. But in this case, because we're not asked to use summation notation, we could just say negative 6, x to the negative 4. Okay, so then that's all we need, and probably want to get rid of the negative exponents on these so we can evaluate them. So negative 1 over x squared, 2 over x cubed, negative 6 over x to the 4th, and then let's evaluate everything at 2. So we get 1 over 2 for f of 2, for f prime of 2, negative 1 over 2 squared, or negative 1/4. You know, normally I wouldn't say negative 1/4. I would say leave it as negative 1 over 2 squared, because you want to preserve the power. But because it's a polynomial, once again, makes it we're a little bit more liberal. So f double prime of 2 is 2 over 2 cubed. And again, I would say normally leave that, but 2 over 8, which reduces to 1/4. And f triple prime of 2, negative 6 over 2 to the 4th. That's negative 6 over 2 to the 4th is 16, which reduces to negative 3/8. Okay, so now we're ready for our substitution. And here's our definition for p sub 3 of x. And so it's f of c, that's 1/2. plus f prime of c, that was negative 1/4, so I'll write negative 1/4 times x minus c, so make sure in this formula x is the only thing that stays, so substitute in the function and its primes evaluated at that value of c, and so what we're substituting in is the function and its derivatives evaluated at c, and then don't forget to substitute in the values of c as well. But again, the x's stay to define the polynomial. So we had f prime of 2, f prime of c, x minus c is 2. Next term, plus f double prime was 1/4 over 2 factorial times x minus c, which is 2 quantity squared, and then plus f triple prime, so that was a negative 3/8 over 3 factorial, and then times x minus c, which is 2 again, quantity cubed. And at that point, you want to simplify these terms, the complex fractions. You don't want to do anything with the first terms. You want to leave the 1/2 and leave the negative 1/4 out in front of the binomial x minus 2. It's not necessary to distribute that, even though we're not writing an infinite polynomial. We do like to see the patterns of that binomial that's being raised to the powers in the subsequent terms. Okay, here you have 1/4 times 2 factorials 2, so times 1/2, so that gives 1/8, and then times the x minus 2 that's being squared, and then finally minus, okay, 3/8 over 3 factorial 6, so that's 3/8 times 1/6, then you can cancel the 3 and the 6, and we get 1/16. And that's x minus 2 as a quantity cubed. Okay, so that polynomial approximates the function 1 over x, just like we saw earlier, where the e to the x, if we graphed the terms, they match the function. And so, as a second example, again, it's just a matter of the function and its first 3 derivatives, and then in a second column we'll evaluate those at the given value of c, which in this case is pi over 4. Okay, so 3 derivatives here. F prime of x would be the minus, the derivative cosine is minus sine, so minus sine of 3x, derivative of the argument 3, put that in front. F double prime of x, okay, we'll leave the minus because the derivative of the sine is positive cosine, and so cosine 3x. And if we were asked about summation notation, I'd tell you to write 3 squared here, but because it's just a polynomial, we're not concerned about preserving patterns or powers, so just another factor of 3 makes it negative 9. And then the third derivative would be now positive, because the derivative of cosine is minus sine, so the double negative makes positive, sine of 3x, and then the derivative of 3x, which is 3, makes the new coefficient 27. Alright, so now evaluate each of these at pi over 4. So this would be the cosine of 3 times pi over 4, or 3 pi over 4. And then you'd probably want to convert, let me go off to the side here. You want to convert 3 pi over 4 to degrees by multiplying by the unit conversion factor, of 180 over pi, and then the pi's cancel, and 4 goes into 180 45 times, so 45 degrees, and then 3 times 45 is 135. Okay, so that's the same as the cosine of 135 degrees. Now we want the exact value, and so therefore I'm going to go down here, and for my exact value, I'm going to draw the Cartesian system. 135 is in the second quadrant, so just draw some terminal side in the second quadrant. So there's the angle of 135 degrees. Pick a point, drop a perpendicular, always to the x-axis. That creates our reference triangle, right triangle. And this angle must be 45, and then similarly this angle must be 45. And the relationship in a 45, 90 is 1, 1, and the square root of 2 for the hypotenuse. But remember, the way I do my trig, you can do it any way you want, but the way I do it, I label these legs with respect to their sense of direction. That is, this is vertical legs in the positive y direction, so I'm going to leave that as positive, but my horizontal leg is in the negative x direction, so I'm going to label that as negative. And then the cosine of 135 is adjacent, -1 over hypotenuse, square root of 2. And probably want to rationalize that to get minus square root of 2 over 2. Okay, so now f prime of pi over 4 is -3 sine of 3 pi over 4. So that's -3 sine of 135 degrees. So -3. Okay, here we found cosine of 135 was -1 over radical 2, which, here, let me rationalize it here, so we don't have to do so in the future. So negative radical 2 over 2, and the cosine of 135, excuse me, the sine of 135, that's opposite over hypotenuse, so now it's the positive 1 divided by the square root of 2. And let me rationalize that, because we're going to be using this over and over. Well, not over and over, but another time when we make our substitutions here. Okay, so that's -3 and then times, I'll just use that, radical 2 over 2. So -3 radical 2 over 2. Okay, and then f double prime of pi over 4 is -9 cosine 3 pi over 4. You know what the cosine is, you can plug it in now. But if you want to show negative cosine 135, then that's -9 times, okay, cosine was a negative radical 2 over 2. So we get positive 9 radical 2 over 2. And then finally for the third derivative at pi over 4, 27 sine of 3 pi over 4, 27 sine of 135 if you want, or skip steps. 27 sine of 135 was radical 2 over 2. Again, we did the work down here. So that gives 27 square roots of 2 over 2. Alright, so now we're ready to plug into the definition. I've got enough room to repeat it. It was p sub 3 because it's the Taylor polynomial of the third order. F of c plus f prime of c times the binomial quantity x minus c plus f double prime of c over 2 factorial times the binomial x minus c squared, and then plus f triple prime of c over 3 factorial times x minus c as a quantity cubed. Okay, so now it's just a matter of substitution. So p sub 3 of x is f of c was the negative radical 2 over 2. Plus f prime of c was negative 3 radical 2 over 2, but times x minus c, and c, recall, was pi over 4. And then plus f double prime, 9 radical 2 over 2, but divided by 2 factorial, times x minus c again was pi over 4 as a quantity squared, and then plus f triple prime, which was 27 square roots of 2 over 2 divided by 3 factorial times x minus c is pi over 4 again, but as a quantity cubed. Okay, and then finally we get p sub 3 of x is equal to, again, these first two terms I'm just going to leave, minus radical 2 over 2, minus 3 radical 2 over 2. That's about to be multiplied by the x minus pi over 4. Don't distribute that, just leave it. But then plus, okay, here, again, if you have to, off to the side, this is going to be our solution, but the 9 square roots of 2 over 2 divided by 2 factorial, which is 2, is the same as multiplied by 1/2. So 9 radical 2 over 4 times the x minus pi over 4, it's being squared. And then similarly here, okay, 27 radical 2 over 2 divided by 3 factorial is 27 square roots of 2 over 2 divided by 6, which is 27 square roots of 2 over 2 times 1/6, and then the 6 and the 27 can cancel. 3 goes into 6 twice, into 27 9 times. So we get 9 square roots of 2 over 4. So plus 9, similar, same thing as the last one. Square roots of 2 over 4, and then x minus the pi over 4 is being cubed. Okay, so for Taylor polynomials, you don't have to worry about preserving powers. And again, it's just an exercise in finding some derivatives, evaluating them, and substituting them improperly into the definition. Alright, so we'll come back and finish up with a couple more examples of Taylor series, and then that'll take care of these 3 topics. So we'll see you when you're ready.